Hi everyone and welcome to this lesson. In this lesson we're going to be looking at what are structures. So quite simply, a structure is a group of variables that can be mixed types that are bunched together in a structure, and you can instantiate that structure so you can access it via a normal variable. So just as you would for a boolean or a byte, you would create your variable name and then create it as a data type of your structure. And then you can access everything inside that structure by first accessing the variable you declared that structure as. So structures can be mixed, like I said, and they accept almost any data type, including other structures. So you can nest structures. Now, how far you can nest depends on the PLC platform that you're using and the PLC hardware that you're using. Some go much deeper than others, and some don't go very deep at all. So let's have a look at a typical non-structured program. And by typical, I mean a sort of beginner's level introduction to a PLC, and everything is loose. There's no rigid structures in how things are laid out. So in this example, we have tags and variables at the top in the blue box, and they're all just loose. Nothing binds them together other than the person who's created these tags has put motor_1 at the beginning and tank_ at the beginning of any tank related tags. And you can see that they're used in a loose fashion in the PLC as well. So in the purple box there, we have a main PLC program object. And now, depending on what PLC you're using, this could just be a program POU, or in the case of Siemens, OB1, for example. And what's happened in this particular case is they've just used motor_1_ auto, tank low, motor1 failed. But the point is that they're directly accessing those tags in the logic in OB1. So there's no wrapper function around this. If we were to have to extend this, or if this was used in multiple places for multiple pumps, any changes that are required to this rung would have to be made in multiple places throughout the program, including new tags that are required for new motors, etc., etc. So tags that are loose rely on naming conventions, typically in order to have some structure around tags. For example, you wouldn't have two motors with completely different tags. It tends to be that you'll have motor 1 and then the item, motor 2 and then the same item, which is the most common form of organization. So let's have a look at a structured example. So in this example here, it's quite simply made up of two global data lists, or data blocks if you're from Siemens. And inside these I have a variable called motor1 in the global data motors, and a variable called tank1 in the global data tanks. Now, just to keep things simple, I'm only showing the motor structure, which is here. So in this blue box here, we have a structure called motor, which has these variables listed inside. Now again, just to keep things simple, I haven't put the data type, but they are all booleans in this case. And then what's happening in our logic now is, you can see we are accessing it via motors.motor1.auto and tanks.tank1.low. So this logic is exactly the same as it was in our previous example of the unstructured data. However, now we have a structured approach of, if we go to our motors global data, we have motor1, which is a motor data type, and we know that that's going to have auto, failed, manual, off. It's going to have all that stuff in there just because it's been declared as a motor type. Now, if we were to go on to expand this and have more than one motor, all we would need to do is add motor_2 into our motors global data and give it the data type of motor. So the reason why this is more efficient is because you're standardizing your data. So once you're happy that a structure has everything that you need it to have inside, you can create multiple instances of that under different names and know that it has everything that you need in there to work with any logic sets that you have or function blocks that you've already created. So accessing the data is pretty straightforward. It's no different really to accessing instance data. So if I want to access this motor one on variable, it's going to be motor_1.on, and if it was motor 2, it'd be motors.motor_2. So it isn't a hard concept to get your head around. But just bear in mind that if you have nested structures, you might have multiple sort of areas to put before the element that you want to look at. So let's take this a step further now, and this is really starting to show why structures are worth doing, as opposed to what structures are. But this example here is showing the same code that we've seen in the previous two examples, but now it's containerized in a function block. So what we have here is our auto, low, and failed that we saw from the previous examples. Notice that they're no longer looking for motor 1 or tank 1 or whatever the prefix for tank is. They're now looking at interfaces here on the function block, which are called motor data and tank data. So what I have right at the beginning of the project, because we are always going to have these sort of loose tags or where our information comes into our PLC on our I/O. This motor 1 running tag here is being mapped into our structure for motor 1. So we bring motor 1 running in and motor 1 failed in, and that gets mapped to our running and failed elements in our motor 1. So we're seeing two different areas of the project accessing this global data here, and this will become more apparent as we go through the course what this means. But essentially what it's showing here is that once we have the information in our structure, we can then go on and use it in other function blocks, and all that we're passing in this case is the structure. So there's no loose information coming into this function block. This function block's only got two in-outs, so only two elements on the interface, so it's much cleaner. And the nice thing about it is if you try to pass the wrong element, the function block won't accept it. So just like if you try and pass a real value to a Boolean value, the compiler says, I can't do that. This is doing the same thing, but with your custom structures. So from a architecting point of view, where you might have a more senior programmer developing function blocks for more junior programmers, it sort of ensures that one of those stepping stones of am I passing the right information to my function block is made much, much easier through structures. Not only that, you can then drop many different instances of this tank and motor control function block and then pass, motor 1, motor 2, motor 3, motor 4. You could pass tank 1 in all of those instances, or pass a different tank for different tanks controlling that function. So you get a bit more of mix and match going on in terms of the structures that you're sending, without the complicated 20-pin interfaces that some people might be more accustomed to using. So the other benefit about using structures, which isn't immediately apparent, is that if I was to go on and add to my structure, so we start using a new piece of equipment, and that piece of equipment has two additional options, for example. We add them into our structure. These interfaces on function blocks will automatically grow, whereas usually what would happen if you weren't using structures is you would then have to go and modify that interface to add those two additional inputs, and everywhere else that information is used if it's required. Whereas now you're using structures, it automatically grows as part of that structured interface. Don't confuse that with not having to reinitialize or being able to do online edits as a result. Siemens and Codesys will still warn that the interface has been changed, and will warn of things going wrong if you try to do online downloads. But you don't have to go and do that programming and make those mistakes where things get missed. So to summarize what a structure is, it's quite simply grouped elements under a name.